Chapter 17, Sound Waves. Sound is a mechanical longitudinal wave. All mechanical waves need media to propagate. The so-called media, we can have gases, liquids, or solids. And the longitudinal wave, mainly in this case, is caused by pressure difference. Well, we learned before, waves that we can use a couple of physical quantities to describe it. Number one is its frequency. Well, in this case, that we categorize sound wave as ultrasound, audible sound, and infrasound. If we look at this frequency scale, between 20 to 20,000 Hertz, if we have enough intensity, then the sound is audible to human ears. Above 20,000 Hertz, and we name this as ultrasound. Under 20 Hertz, and we name it infrasound. Well, dogs will be able to hear ultrasound, and elephants will be able to hear infrasound. And for human ears, that we need a frequency range from 20 to 20,000 Hertz. I mentioned if we have enough intensity and if we have the right sound frequency range, then it's audible. The sound waves will be audible to human ears. Intensity is proportional to the amplitude of square. What amplitude? Well, when we learn waves, we know that there is amplitude and frequency. So that wave amplitude, which means the displacement of the media particle. Now, sound travels at certain speed. It really depends on the temperature of the media. And we're going to learn what physical quantities determine the speed of sound waves. This is a thin, long tube filled with a kind of fluid. Well, when we talk about fluid, it could be gases or liquids. And the area with more dots indicating a compressional zone. And area has less dots indicating this is a regular uncompressed zone. Now imagine that just for simplicity, a single compressional pulse produced by a single stroke of piston is sent down a long tube with speed v. Say, for example, this is the compressional pulse, which travels from left to the right. Assume that the pulse has sharply defined leading and trailing phases. If the pulse travels from left to the right, this will be leading, this will be trailing. Assume it has sharp defined phases, and that is has uniform pressure and density in its interior. Uniform pressure and density in its interior. Well, in order to derive the speed of sound, it is more convenient that we choose a reference frame in which the pulse remained stationary while the fluid moves through it from right to the left. This is a relative motion. So actually, if the compressional pulse travels from left to the right, if we assume the pulse doesn't move, then the rest of the fluid flows from right to the left. So we're going to choose such a reference frame that the compressional fluid, this compressional pulse, remains stationary, and the rest of the fluid travel towards this compressional zone. So imagine that we cut a slice of moving fluid element of length delta x. The leading phase travels at speed of v. Since we choose the moving direction is from right to the left, so v is positive. The cross-section area of this slice is capital A. And right now, the fluid has pressure of P and obviously moving at speed of v from left to right. Well, this compressional zone, once the slice of fluid enters, that the front of the face will encounter a P plus delta P, which is higher pressure, and the trailing face will still remain outside. This will cause a problem. That is, there is a compression for this slice of fluid. If the left edge of the fluid element enters the compression zone at the time t, and the right edge that enters the compression zone at the time of t plus t, there is a time delay. That the time interval delta t equals the length of the slice divided by speed of the slice moves. Well, obviously, this is calculated while this slice is still outside. This is the time for this moving fluid element enters compressional zone, so it will still keep the same v and the distance delta x. Now, let's take a look at what happened. The leading phase encounter a P plus delta P, which is high pressure. This is leading. The trailing is still remain outside, so pressure is still P. If we use the pressure on the left side times the cross-section area A, there is a resistance force to the leading edge. And then the trailing phase will encounter a P time cross-section area a force which pushes this moving fluid element. Well, we know that P plus delta P time A is bigger than P time A. So the net force, well, since we already decide to the left is positive, and then that force will be negative. So the net force is the addition of these two forces, then that will be P times A and plus that negative force, which is actually minus P plus delta P times A. And the net force comes out as negative delta PA. The net force is negative, which means the net force F net resists this slice of moving fluid, enters this compressional zone. This will cause a deceleration. According to Newton's second law, that a net force suppose equal to mass time acceleration. In this case, acceleration is a deceleration because the force actually resists this moving fluid element enters the compression zone. Acceleration will be delta V over delta T. Since it's deceleration, our delta V is negative, which means this moving fluid element will slow down. The original length of this slice is delta X. Cross-section area is A. So the original volume of this slice of moving fluid is that the length delta X times cross-section area A, that gives it volume. If undisturbed density we name is rho, then the mass of this slice will be density times its original volume. That will be rho delta X times A. Now, we already know that our net force F net equals to mass times deceleration delta V over delta T. So mass is rho delta XA and deceleration delta V over delta T. And also we got the net force is the difference of the force that P plus delta P times A and that P times A. So the net force, as a matter of fact, is negative delta P of A. Look at this equation. If we cross the cross-section area A from left and the right, and we rewrite this equation, what we have is rho v squared and equals to delta P over delta V over V. If you have a question, where did this delta X go? Well, as we know that the time delta T between the leading phase and trailing phase enters compressional zone has a relationship of the length of the moving fluid element over its speed V. So actually we replace delta X by delta T times V right over here. This is why we get this V squared. During the delta T second, when this slice of flowing fluid get into the compressional zone, that the leading edge will travel at the speed V plus delta V. Well, we know it slows down because delta V is negative. So therefore, the leading phase travels a distance of its speed time to time. The trailing phase still travels the same speed V because it's still outside the compressional zone, and so therefore travel distance of that. Therefore, this slice of fluid gets compressed because the leading phase travels slower than the trailing phase. So the difference between these two is delta V of delta T, which means the slice gets thinner. This is the change of volume. So therefore, change of volume delta capital V is the shortened length of this flowing fluid element times cross-section area. Now, if we look at the ratio of change of volume over volume, since we know change of volume is delta V, change of speed, time interval, time cross-section area. The original volume, as you know, is that this length delta X times A. And on the other hand, that delta X is delta T times V. So it's actually V delta T times A. Now, obviously, delta T and A cancels. Then we get delta V over V, which tells us the ratio of change of speed equals the ratio of change of volume. That makes sense. So we're going to replace that the ratio of change of speed into this equation. So this equation becomes that density rho times speed of the fluid flowing equals to negative delta P over, right now will be delta volume over volume. If we remember our chapter of 12, section 4, about the definition book modules, the negative change of pressure over the ratio of change of volume defined as the book modulus. Therefore, speed of the fluid flowing equals to square root of book modulus divided by density of the fluid. Well, if we recall our definition that from the very beginning, as a matter of fact, the compressional pulse travels from left to the right with the speed of V. This actually is how fast this compressional signal travels. That is the speed of sound. Now, if we take this as a reference, assume this is stationary, and then the fluid flows to the left. Therefore, the speed of fluid flow to the left, as far as the magnitude concerned, is the same as the compressional pulse travel to the right. So what we get here is the speed of the moving fluid. That is equivalent to the speed of sound. So our conclusion is speed of sound equals to square root of book modulus of the fluid divided by its undisturbed density, rho. Well, this is a very interesting result, and I want to point out a couple of things. If the media through which the pulse travels is a thin solid rod rather than a fluid, then we need to replace this Book modulus with Young's modulus, because if we consider a thin solid rod. And also, if the solid is extended, for example, that is a drum, the face of the drum, that's two-dimensional. In that case, we have to not only consider Book modulus, but we also have to consider shear modulus, if you remember your chapter 12. So there's a lot more about the speed of sound, travel around a two-dimensional surface, or even travel through a three-dimensional solid. Well, speed of sound also depends on the temperature. So there is such a relationship that we can determine the speed of sound. Well, in this equation, that speed of sound is 331 meters per second times the square root of 1 plus temperature, room temperature, or the temperature of the fluid, divided by that 273 degrees Celsius. And so as long as we know the temperature of the fluid, say for example, if we concern about the sound travel in the air, then we use the temperature of the air. Otherwise, if concerned the speed of sound through the liquid, then we use the temperature of liquid. But it must be in Celsius, and then divide by 273 degrees of Celsius. That gives us a result for the speed of sound for that particular temperature. Now, on page of 514 of your textbook, there is a table 17.7. Actually 17.1, and it gives us the speed of sound in various media. And we have media of gases like hydrogen, helium, and air. If we take 0 degree hydrogen, we will get the speed of sound very high. Speed of sound in the hydrogen is around 1,286 meters per second at 0 degrees Celsius of hydrogen. And then if we take a look at speed of sound in the helium, at the same 0 degrees Celsius, then it slows down to 972 of meter per second. So it really depends on the what kind of media, because that associated with its density.